4 billion years ago, our sun was a cosmic infant, a dim, sputtering furnace that pumped out a staggering 30% less heat than it does today. Every calculation screams it. Our planet should have been a frozen tomb, a desolate snowball locked in an eternal ice age, utterly barren. But the rocks, the fossils, the very history etched into Earth's ancient crust, they tell a different story. A story of liquid oceans churning, of rivers carving canyons, of life itself exploding across a warm, watery world. How did our fragile blue marble defy the impossible, hiding a profound cosmic secret for billions of years? For billions of years, our sun has raged, a thermonuclear titan anchoring our entire solar system. But rewind the cosmic clock back to when Earth was a mere toddler, barely a billion years old. Our star, the very heart of our existence, was a different beast entirely. Stellar evolution models, the ironclad blueprints of how stars ignite, live and die, paint an undeniable portrait. The young sun, approximately 4 billion years ago, shone with a pathetic, anemic glow. It was a cosmic furnace operating at a mere 70% capacity, a pale shadow of the blazing orb that warms our world today. This isn't some abstract theoretical wobble. It's a fundamental prediction, a mathematical verdict handed down by the very laws of physics. Less mass had fused into helium in its core, meaning fewer nuclear reactions ripped through its heart, meaning less raw energy streamed across the vast emptiness to our nascent planet. The consequence was brutal, inescapable. Earth, bathed in this feeble light, should have plunged into a deep freeze. Its oceans, its very lifeblood, should have solidified into a planetary ice cube, utterly barren, utterly dead. Imagine a world encased in kilometers of ice, a silent white sphere hurtling through the black. That was our planet's ironclad destiny, according to the numbers. But then the universe spoke back, and its voice was a thunderous geological rebellion. From the deepest, most ancient rock formations, from the very core of Earth's primordial history, evidence screamed defiance. We found pillow lavas, volcanic rock that can only form when molten rock erupts underwater, instantly cooling into bulbous, pillow-like shapes. We unearthed sedimentary rocks, laid down by flowing water, layer upon ancient layer, chemical signatures, locked within isotopes, whispered tales of vast liquid oceans, not frozen wastes. There was even undeniable proof of early life, ancient microbial mats, stromatolites, clinging to existence in warm, shallow seas. The data was unequivocal. Liquid water flowed freely across the surface of a young Earth, even as the sun's faint light barely kissed its atmosphere. This wasn't a minor discrepancy. It was a cosmic paradox, a brutal contradiction that ripped a gaping hole in our understanding of stellar physics and planetary climate. Cosmology reeled, physics screamed. How could two fundamental truths, a faint young sun and a warm, wet Earth, possibly coexist? It was an impossible riddle, a cosmic accusation against our scientific models, and it brought the entire field to its knees. The universe had delivered a profound, impossible question, and we had no answer. Faced with this cosmic contradiction, this impossible riddle of a warm, wet Earth under a faint, cold sun, scientists launched a desperate gambit. If the sun wasn't pumping out enough heat, then Earth itself had to be holding it in. The prime suspect, the planet's first and most desperate line of defense, became its early atmosphere. We needed a blanket, a colossal, invisible shield to trap every precious photon of the sun's anemic light. And the only gas capable of such a monumental task, the only cosmic heat trap powerful enough, was carbon dioxide. Picture it, a young Earth, shrouded not in the thin, transparent veil we breathe today, but in a suffocating, dense shroud of CO2. We're talking about an atmosphere so thick, so rich in greenhouse gases, that it would make Venus look like a breezy afternoon. Models began to churn, desperately calculating the sheer volume of carbon dioxide needed to counteract the sun's weakness. The numbers were staggering. To keep the oceans liquid, early Earth would have required CO2 concentrations hundreds, even thousands of times higher than today's levels. Imagine breathing that. It would have been a choking, acidic inferno by modern standards. Yet for the planet, it was a life-saving embrace. this wasn't just a convenient assumption. It was rooted in the very geology of a young, tectonically active Earth. Volcanic eruptions, far more frequent and violent in the planet's infancy, would have belched vast quantities of CO2 into the atmosphere. The carbon cycle, the planet's fundamental regulator, would have been operating at a furious pace, with no complex life to sequester carbon, and vast amounts constantly venting from the churning mantle. A super greenhouse effect seemed plausible. Early Earth wasn't just warm, it was potentially a steamy primordial pressure cooker, its surface obscured by thick, CO2-laden clouds. But even this desperate gambit faced brutal challenges. How much CO2 could the early Earth really hold? Geochemical evidence from ancient rocks, particularly paleosols, fossilized soils, suggested limits. If the CO2 levels were too high, they would have created an atmosphere so acidic that it would dissolve silicates in rocks at an unprecedented rate, locking carbon away and cooling the planet again. It was a delicate, terrifying balance. The planet needed immense amounts of greenhouse gas, but not so much that it triggered its own cooling mechanisms. It was like trying to balance a skyscraper on a needle, a desperate, high-stakes atmospheric tightrope walk. The sheer scale of the required CO2 pushed the limits of our atmospheric models, forcing us to question the very assumptions about early Earth's geochemistry. This wasn't just a simple fix, it was a radical reimagining of our planet's primordial state. If you're finding this cosmic detective story as mind-bending as I am, smash that like button and subscribe. We're just getting started. The carbon dioxide solution, while plausible, felt like a single, massive lever pulling against an equally massive paradox. Scientists knew Earth's early atmosphere, its desperate gambit, likely involved more intricate mechanisms, a symphony of invisible architects working behind the scenes. The planet wasn't just relying on one heavy blanket, it was knitting a complex, multi-layered shield, and one of the most powerful, yet often overlooked players in this ancient drama was methane. Methane, a greenhouse gas far more potent than CO2 on a molecule-for-molecule basis, could have provided the extra punch needed to warm the faint young Earth. Picture colossal swamps, teeming with the earliest, most primitive microbial life, methanogens, churning out vast quantities of this invisible, super-warming gas. In an oxygen-poor early atmosphere, methane wouldn't break down as quickly, allowing it to accumulate to levels that could drastically ramp up the planet's temperature. It was Earth's hidden ace, a potent atmospheric secret weapon. But this too came with a terrifying catch. Too much methane could lead to the formation of a high-altitude organic haze, a smog layer that would reflect sunlight back into space, actually cooling the planet. It was a razor's edge, a delicate dance between warmth and frozen oblivion. Beyond these individual gases, Earth itself demonstrated a startling, almost intelligent capacity for self-regulation. The planet's own systems, its geological heartbeat, seemed to be actively working to maintain warmth. One crucial feedback loop involved what we call weathering. When CO2 dissolves in rainwater, it forms carbonic acid, which then reacts with silicate rocks, effectively pulling CO2 out of the atmosphere and locking it away. This process acts as Earth's thermostat. If the planet gets too hot, weathering speeds up, drawing down CO2 and cooling things. But if it gets too cold, weathering slows down dramatically, allowing volcanic CO2 to build up and warm the planet. In the faint young sun era, with lower temperatures, this thermostat would have been dialed down, allowing CO2 to accumulate to the necessary sky-high levels. Another invisible architect, clouds. The early Earth's atmosphere might have been a swirling canvas of different cloud types, each playing a critical role. Low-lying, thick clouds could have reflected incoming solar radiation, cooling the planet, but high-altitude, thin cirrus clouds, composed of ice crystals, could have trapped outgoing infrared radiation, contributing to a powerful greenhouse effect. The precise balance of these cloud formations, driven by atmospheric dynamics we're only beginning to understand, would have been critical. It's a complex, dynamic system where tiny changes in cloud cover could tip the scales between a habitable world and a frozen wasteland. This wasn't just a passive acceptance of cosmic fate. Earth, in its infancy, seemed to possess a hidden planetary intelligence, a suite of interconnected processes that actively fought against the sun's weakness. It was a testament to the planet's astonishing resilience, a complex dance between geochemistry, atmospheric physics, and the earliest stirrings of life, all conspiring to keep our cosmic cradle warm. The mystery deepened, revealing not a single simple solution, but a beautiful, terrifyingly precise orchestration of natural forces. The faint young sun paradox, this cosmic accusation against our planet, refused to yield to simple explanations. It demanded a broader canvas, a deeper dive into interconnected forces beyond just atmospheric gases. The solution, we now suspect, wasn't a single heroic champion, but a cosmic conspiracy, a subtle symphony of interlocking players working in concert to keep Earth from freezing solid. One often overlooked factor was Earth's albedo, its reflectivity. Imagine a pristine white snowball versus a dark, rocky sphere. The snowball bounces almost all sunlight back into space, staying frigid. The dark rock absorbs it, warming up. Early Earth, with less landmass and potentially more widespread dark volcanic rock, might have had a lower albedo, absorbing more of the sun's meager warmth. But what if early cloud cover, or even the formation of vast, dark oceans, which absorb more heat than reflective ice, played a role? It's a subtle adjustment, but in the knife-edge balance of the early climate, even a slight shift in reflectivity could have been critical. Then there's the possibility of subtle shifts in Earth's orbital mechanics, while the sun's output was fixed. What if Earth's orbit was slightly different, or its axial tilt varied in a way that maximized solar insolation during critical periods? These are minute tweaks in the cosmic clockwork, but over millions of years, they could have offered fleeting moments of warmth, enough for the planet to avoid a runaway freeze. It's a less favored hypothesis, given the stability of orbital dynamics. But in the realm of planetary survival, every possibility is wrestled with. But here's the most radical, mind-bending twist in this cosmic conspiracy: the potential role of early primitive life itself. We often think of life as a passive passenger, evolving, because the planet is habitable. But what if life was an active architect of habitability, a key player in preventing Earth's frozen doom? The earliest microbes, the methanogens we discussed, weren't just producing a potent greenhouse gas. They were actively shaping the atmosphere. Their metabolic processes could have dramatically altered the balance of atmospheric gases, creating a feedback loop that kept the planet warm. Imagine these microscopic pioneers clinging to existence in hot springs and shallow seas were unknowingly engineering their own survival. They were not just adapting to the environment, they were actively terraforming it. This concept, often called the Gaia hypothesis, suggests that life and its planetary environment co-evolve, intricately linked in a self-regulating system. In this view, the very presence of liquid water and the conditions necessary for life were not accidental. They were, in part, a consequence of life's own desperate struggle to persist. The ultimate reveal, then, is not a single, elegant solution, but a tapestry woven from countless threads: a thick, CO2-rich atmosphere, boosted by potent methane, a planetary thermostat in the form of silicate weathering, the intricate dance of cloud formations, subtle shifts in reflectivity, and perhaps most profoundly, the earliest, most tenacious forms of life actively shaping their own destiny. It was not one hero, but a symphony of interconnected forces, a grand cosmic collaboration that allowed our fragile blue marble to defy the odds and bloom with life. Even under the anemic gaze of a faint young sun, the universe, it seems, has a deeper, more intricate story to tell than we could have ever imagined. Our journey through the faint young sun paradox shatters the comfortable notion of a passive, indifferent cosmos. It reveals a universe of astonishing precision, a terrifyingly delicate balance of forces that allowed our planet to escape an icy grave. We've seen how stellar physics demanded a frozen Earth, while geological evidence screamed for liquid oceans. And in that profound contradiction, we uncovered a cosmic ballet of atmospheric gases, planetary feedback loops, and even the earliest stirrings of life, all conspiring to defy the impossible. This isn't just a tale of ancient Earth, it's a profound meditation on the resilience of existence itself. It reminds us that the conditions for life, for consciousness, are not merely statistical flukes, but the outcome of an intricate dynamic interplay of cosmic forces. Our home, this vibrant oasis in the vast cold dark, is a testament to an intricate dance of defiance, a triumph against cosmic odds that still humbles our understanding. The universe in its indifference also holds secrets of improbable tuning, hinting at a deeper, more profound narrative than we often dare to consider. We are here not by random chance alone, but by a complex, interwoven tapestry of cosmic coincidences and planetary self-preservation. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.